MIPS register file explained how 32 registers feed the CPU. Welcome back to Gate and Kernel. Inside every processor, instructions are constantly reading values, performing operations, and writing results. But where does the CPU keep the data it needs right now? In a classic MIPS processor, much of that immediate working data lives inside a small but extremely important structure called the register file. In this video, we will examine how 32 general-purpose registers are organized, how two operands can be read at the same time, how one result is written back, and why the register file sits at the center of instruction execution. Let us open the CPU and see how the MIPS register file really works. A processor can perform millions or billions of operations every second. It can add numbers, compare values, calculate addresses, control loops, call functions, and move data through a program. Before any of those operations can happen, the processor must obtain the values required by the current instruction. Those values may originally come from memory, but a processor cannot rely on main memory for every simple calculation. Main memory offers a large capacity, but it is much slower than the execution hardware inside the CPU. The processor therefore keeps its most immediate working values in registers. In the classic 32-bit MIPS architecture, the programmer visible integer register set contains 32 general-purpose registers. Instructions identify these registers using 5-bit register fields. In a commonly used single-issue teaching data path, the registers are represented as a register file with 2 read ports and 1 write port. This allows an instruction to obtain 2 source operands and later write 1 result. This article explains both sides of the subject: what the MIPS architecture makes visible to software, how a classic textbook register file can implement that behavior. The distinction matters because the instruction set architecture does not require every physical MIPS processor to use exactly the same internal register file circuit. Chapter 1: What is a register? A register is a small storage location inside a processor. In MIPS32, each general-purpose register holds a 32-bit value. That value may represent a signed or unsigned integer, a memory address, a character or bit field, a mask used by logical operations, a function argument, a return value, an intermediate calculation result. The bits in a 32-bit register are normally numbered from 0 through 31. Bit 0 is the least significant bit. Bit 31 is the most significant bit. Each bit stores either 0 or 1. Together, the 32 bits form one complete binary value. A single register has very little capacity, but registers are directly involved in instruction execution. They hold the values that arithmetic, logical, branch, load, and store instructions use. Chapter 2: Architectural registers and physical hardware. It is useful to separate two related ideas. Architectural registers: these are the registers visible to machine instructions in software. The MIPS32 architecture defines 32 general-purpose registers, numbered from 0 through 31. An instruction can name these registers as sources or destinations. Physical register file hardware: this is the circuit used by a particular processor implementation to provide the required architectural behavior. A simple MIPS processor may implement the registers as one compact array with 2 read ports and 1 write port. A more advanced processor may use additional ports, multiple banks, replicated storage pipeline stages, shadow register sets, separate register contexts for hardware threads, internal physical registers used for register renaming. Software still sees the architectural register set, even when the physical implementation is more complicated. Throughout this article, register file refers mainly to the classic teaching implementation unless stated otherwise. Chapter 3: The 32 general-purpose registers. The classic MIPS32 programmer visible integer register set contains 32 general-purpose registers. They are numbered: register 0, register 1, register 2. Register 31 because there are 32 possible registers. A register number requires 5 bits, 2 to the 5th power equals 32. A 5-bit binary value can represent the numbers 0 through 31. This is why register fields such as RS, RT, and RD in classic MIPS instruction formats are 5 bits wide. The instruction supplies a register number. The processor uses that number to access the corresponding architectural register. This register number is not a memory address. It is a small identifier used inside the processor. Chapter 4: What does 32 by 32 register file mean? A classic MIPS32 register file is often described as a 32 by 32 register file. The first number represents 32 registers. The second number represents 32 bits per register. Conceptually, it can be drawn as a table. Register 0, 32 bits. Register 1, 32 bits. Register 2, 32 bits. Register 31 and 32 bits. When a read address identifies one row, the corresponding 32-bit value appears at the read output. When a write address identifies one row, that register may store a new 32-bit value when writing is enabled. This table is a useful logical model. A rail integrated circuit does not necessarily look like 32 separate rectangular registers connected to giant visible multiplexers. Chapter 5. Does the register file contain only 128 bytes? 32 registers multiplied by 32 bits gives 32 times 32 bits equals 1024 bits. Since 8 bits equal 1 byte, 1024 bits divided by 8 equals 128 bytes. Therefore, the 32 programmer visible MIPS32 general-purpose registers represent 128 bytes of architectural integer state. That does not necessarily mean that a real processor contains only 128 physical bytes of register-related storage. A particular implementation may include shadow copies of the register sets, separate register sets for multiple hardware threads, pipeline storage, test and recovery structures, additional implementation-specific registers. The 128-byte figure describes the information capacity of one visible set of 32 32-bit general-purpose registers. Chapter 6. Why did classic MIPS choose 32 registers? The number of registers is connected to instruction encoding. Classic MIPS instructions are 32 bits long. Many instructions must encode one source register, a second source register, a destination register, an operation code, additional function, or immediate information. 32 registers require 5 bits per register field. This provides a practical balance. More registers could reduce the need to move temporary values to memory, but larger register numbers would consume more instruction bits. Fewer registers would reduce the size of the register fields, but software would have less fast working storage. The MIPS design uses 32 general-purpose registers while preserving a regular 32-bit instruction format. Chapter 7. Register numbers and assembly names. MIPS assembly programmers normally use symbolic register names rather than writing only numerical register identifiers. For example, add T0, T1, T2. The symbolic names make the purpose of the code easier to understand. However, names such as T0, S0, 0, and V0 are primarily part of software conventions and application binary interfaces. They do not mean that the underlying registers use fundamentally different storage circuits. For example, T0 equals register 8, T1 equals register 9, S0 equals register 16, SP equals register 29, array equals register 31. The assembler converts the symbolic names into register numbers before generating machine code. The hardware ultimately works with the encoded numbers. Chapter 8. Common register names in the classic O32 ADDI. The following names and uses are commonly associated with the classic MIPS O32 calling convention. Register 0 is 0, the constant 0 register. Register 1 is AT, reserved for assembler-generated code. Registers 2 through 3 are V0 through V1, used for function return values. Registers 4 through 7 are A0 through A3, used for function arguments. Registers 8 through 15 are T0 through T7, caller saves temporary values. Registers 16 through 23 are S0 through S7, caller saved values. Registers 24 through 25 are T8 through T9, additional temporary values. Registers 26 through 27 are K0 through K1, reserved for kernel use. Register 28 is GP, the global pointer. Register 29 is SP, the stack pointer. Register 30 is FP, or S8, the frame pointer or a saved register. Register 31 is RA, the return address. These uses are software conventions. The architectural exception is register 0, reading it produces 0, and attempts to change it do not produce a persistent non-zero value. Other registers can generally hold either addresses or ordinary data, although software conventions assign them particular roles. Different MIPS ADDIs may use some registers differently, so the table should not be treated as a universal hardware rule. Chapter 9. 2 sources and 1 destination. Many classic MIPS instructions operate on 2 source registers and produce 1 destination result. Consider add T0, T1, T2. Its meaning is T0 equals T1 plus T2. The instruction needs to obtain 2 values, the value stored in T1, the value stored in T2. It then produces one result that is written to T0. This instruction-level behavior naturally motivates a register file implementation with 2 read ports 1 write port. However, the port count is an implementation choice, not an ISA requirement. A classic single-issue data path commonly uses 2 read ports and 1 write port because that structure matches the needs of many ordinary MIPS instructions. A superscalar implementation that issues multiple instructions per cycle may require additional ports, banking, replication, or other techniques. Chapter 10. A classic to read, 1 write register file in the textbook model. The register file has the following interface: read address 1 5 bits, read address 2 5 bits, read data 1 32 bits, read data 2 32 bits, write address 5 bits, write data 32 bits, register write 1 control signal clock. The first 5-bit read address selects one architectural register. The second 5-bit read address independently selects another register. The two selected 32-bit values appear on separate outputs. The write address identifies the destination register. The write data input provides the new value. The register write control signal determines whether the architectural register state should be updated. This interface is simple enough to explain clearly, yet powerful enough to support a basic MIPS data path. Chapter 11. How a read port can be modeled in a simplified circuit diagram. One read port can be represented by a 32-to-1 multiplexer. The values from all 32 registers are connected to the multiplexer. The 5-bit read address controls which value reaches the output. For example, read address equals 8, read data equals contents of register 8. If the address changes, read address equals 16, read data equals contents of register 16. A second independent selection path produces the second read value. The two read ports may select different registers. Read address 1 is equal to 9, read address 2 is equal to 10. They may also select the same register. Read address 1 is equal to 16, read address 2 is equal to 16. Reading does not remove data from a register. It exposes the selected value to the rest of the data path. In a fabricated processor, the internal circuit may be implemented as a dense multi-port array rather than as two literal collections of large multiplexers. Chapter 12. How the write port can be modeled. The classic write port receives a 5-bit destination number, a 32-bit data value. A register write enables signal, a clock. The write address selects the destination. The write data provides the value to be stored. The enable signal determines whether the instruction should modify the general purpose register state. For example, write address equals 8, write data equals calculation result, register write equals 1. This means that register 8 is intended to receive the result. If the register write signal is 0, no ordinary general-purpose register should be updated through that write port. Chapter 13. The 5 to 32 decoder. A simple write circuit can use a 5 to 32 decoder. The decoder converts a 5-bit register number into 32 individual selection signals. For example, input equals 01000. Selected output equals register 8. Only the selected register receives an active write selection signal. That signal is combined with the global register write control. The register is updated only when 1. Its decoder output is active. 2. Register writing is enabled. 3. The required clock event occurs. All registers may be connected to the same write data value, but only the selected destination stores it. Again, this decoder model is a teaching representation. A physical processor may optimize the write selection circuit differently. Chapter 14. Combinational reads and clocked writes. Many textbook presentations of the classic single-cycle MIPS data path model register reads as combinational. In that model, changing a read address causes the corresponding register value to appear at the output after the circuit's propagation delay. The read does not wait for a new clock edge. Register writes are commonly modeled as clocked operations. The write address, write data, and enable signal become stable during the cycle. At the active clock edge, the selected register captures the new value. This arrangement supports a useful sequence. 1. Read the source operands. 2. Perform the required operation. 3. Prepare the result. 4. Write the result at a controlled clock edge. This timing behavior belongs to the classic data path model. The MIPS ISA specifies the visible result of an instruction, not the exact transistor level timing used by every implementation. Pipeline and higher performance processors may organize register access differently while preserving the same architectural behavior. Chapter 15. Following an add instruction, consider the instruction add T0, T1, T2. In a classic MIPS R-type encoding, RS identifies the first source register. RT identifies the second source register. RD identifies the destination register. For this example, RS equals T1 equals register 9 or T equals T2 equals register 10 or D equals T0 equals register 8. A simple data path performs the following steps. 1. Register 9 is selected through the first read port. 2. Register 10 is selected through the second read port. 3. Both 32-bit values are sent to the execution hardware. 4. The arithmetic logic unit performs addition. 5. The result returns to the register file write input. 6. Register 8 is selected as the destination. 7. Register writing is enabled. 8. The result becomes the new architectural value of register 8. At this stage, the ALU can be treated as a black box. Operand A enters the ALU. The ALU produces the result. Operand B enters the ALU. The internal construction of the ALU is a separate subject. Chapter 16. The special behavior of register 0. Register 0 is special in the MIPS architecture. Reading it produces 0. Writing a non-zero value to it does not create a persistent non-zero value. This gives instructions a permanent source of 0. For example, add T0, T1, 0. The result is equivalent to copying the value in T1 into T0, assuming the addition does not introduce any other issue. T0 equals T1 plus 0. The 0 register is useful for comparing values with 0, constructing move-like assembler operations, generating a known 0 input, discarding an unwanted destination result, simplifying instruction encoding. A processor may implement this behavior by blocking writes to register 0, forcing its read output to 0, or using another equivalent circuit. The ISA visible result remains the same. Chapter 17. Immediate instructions. Not every instruction obtains both operands from the register file. Consider add immediate T0, T1, 10. This instruction uses the value in T1, the immediate value 10 encoded in the instruction. The register file supplies the value from T1. The second operand comes from the sign extended immediate field rather than from the second register output. A multiplexer elsewhere in the data path can choose between read data to the extended immediate value. The register file itself does not decide what the operands mean. It simply returns the contents of the requested registers. Control and selection logic elsewhere in the processor determines which values enter the execution unit. Chapter 18. Load instructions. Consider load word T0, 4 from T1. This instruction loads a 32-bit word from memory. The effective address is based on contents of T1 plus signed offset 4. A simple execution flow is 1. Read T1 from the register file. 2. Use T1 as the base address. 3. Add the instruction's signed offset. 4. Request the word from the memory system. 5. Return the loaded value to the register file write input. 6. Select T0 as the destination. 7. Enable the architectural register write. From the register file's point of view, the load instruction reads a base address register, later receives a value from the memory path, writes that value into a destination register. The internal operation of caches, buses, and memory can be studied separately. Chapter 19. Store instructions. Consider store word T0, 4 from T1. This instruction stores the value in T0 to memory. It needs two register values. T1 supplies the base address. T0 supplies the data to be stored. A 2-read port register file can provide both values. Read port 1 reads T1. Read port 2 reads T0. The processor combines the base address with the signed offset to form the effective memory address. The second register value travels toward the memory system as store data. A store instruction does not write a new result into the ordinary general-purpose register set. Therefore, the general-purpose register write control is disabled for the store. This is an important example because it shows that two register reads are useful even when no register write occurs. Chapter 20. The register file is not the entire processor state. The 32 general-purpose registers are only one part of the processor's architectural and microarchitectural state. Depending on the MIPS architecture version and implementation, additional state may include the program counter HI and LO registers, floating point registers, coprocessors, zero control registers, exception and status registers, memory management registers, shadow register sets, hardware thread contexts, pipeline registers, internal implementation registers. The program counter is not normally treated as one of the 32 general-purpose registers. Traditional MIPS multiply and divide operations may use HI and LO, which are also outside the ordinary GP or set. Floating point hardware uses a separate register set when implemented. A modern or specialized MIPS core may therefore contain much more register storage than the basic 32-register architectural model suggests. Chapter 21 registers are not cache registers, and cache both keep data close to the execution hardware, but they are controlled differently. Registers are explicitly named by instructions. For example, add T0, T1, T2. The instruction directly identifies the source and destination registers. Cache normally holds copies of blocks from the memory address space. Programs usually access memory addresses, while cache hardware automatically determines whether the required block is already present. Software does not ordinarily name a particular cache line in an arithmetic instruction. Registers hold individual working values selected by instructions. Cache holds portions of the memory hierarchy selected and managed largely by hardware. The two structures are related to performance, but they serve different architectural roles. Conclusion: the classic MIPS32 architecture exposes 32 general-purpose registers, each containing 32 bits. 5-bit instruction fields can identify any register from 0 through 31. Register 0 always provides the value 0. Common names such as A0, T0, S0, SP, and R come largely from software calling conventions rather than from physically different kinds of registers. In the classic single-issue teaching data path, the register set is commonly represented by a register file with 2 read ports, 1 write port, 2 5-bit read addresses, 1 5-bit write address, 2 32-bit read outputs, 1 32-bit write input, a register write control signal. This structure matches the needs of instructions that read 2 source registers and produce 1 destination result. However, 2 read ports, 1 write port, combinational reading, and edge-triggered writing are features of the teaching implementation, not universal requirements imposed on every physical MIPS processor. More advanced implementations may use different internal structures while presenting the same architectural register behavior to software. The register file does not perform arithmetic or logical operations. Its job is to hold programmer visible working values, supply operands to the execution hardware, receive results produced by instructions. After the operands leave the register file, they commonly enter the arithmetic logic unit. That makes the ALU the natural next component to study. The MIPS register file is small, but it plays a central role in almost every instruction. It holds the processor's immediate working values, supplies operands to the execution hardware, and receives results after an operation is completed. In the classic teaching data path, 2 read ports allow 2 source registers to be accessed at the same time, while 1 write port returns a result to the destination register. But the register file itself does not perform the calculation. That job belongs to the arithmetic logic unit, or ALU. In the next episode, we will open the ALU and see how digital circuits perform addition, subtraction, comparisons, and bitwise logic. This is Gate and Kernel. Thanks for watching, and I will see you in the next one.